We must now turn our attention to the subject of electric power. We already know that electric current is the movement of electrons through a conductor, and that there is a force, the electromotive force, driving the electrons through the circuit. We shall now be thinking about the work done by that current and the power absorbed in doing that work. But first, what is work? Well, in science, work is done whenever a force causes motion. For example, when the force of the expanding steam in the cylinder drives the steam engine, or when the force of the hammer drives in the nail, or of course, when the electromotive force drives the electrons around the circuit. Now, suppose we have a steam engine being driven slowly. It will be doing a small amount of work. But if it is driven faster, it will be doing more work. It will be working at a higher rate. The rate at which work is done is called power. In an electric circuit, the power, the rate at which work is done, depends on the number of electrons moved and the speed at which they travel. But the number of electrons moved is the current flowing in amps, I. And the speed at which they travel depends on the voltage, V, driving them around. So P, the power absorbed in the circuit, is given by V times I, volts times amps, and is measured in watts, W. This is the power formula. P equals VI. We don't always have to say times I. P equals VI is enough. For example, in this circuit, V equals 100 volts, and I equals 2 amps. So the power absorbed, P equals VI, that is 200 watts. Or again, this electric heater is connected to a voltage supply of 250 volts and is passing a current of 4 amps. The power absorbed by the heater is 250 times 4. That is 1,000 watts, 1 kilowatt. It's a 1 kilowatt heater. There are other ways of expressing the power formula, P equals VI. You remember the Ohm's law triangle, from which we can say that V equals IR. So if in the power formula we put V equal to IR, it simplifies to P equals I squared R. Similarly, I equals V over R. And if we put this value for I in the power formula, we get P equals V squared over R. So we have 3 ways of expressing power. P equals VI, P equals I squared R, and P equals V squared over R. These are all very useful formulae and should be learned by heart. Perhaps we should try a few examples. You might want to calculate the power absorbed by a resistor R when the applied voltage is 20 volts and the current flowing is 4 amps. Well, P equals VI, which equals 20 times 4 equals 80 watts. Or again, suppose we have a 50 ohm resistor with 5 volts across it. What power is being absorbed? We know R and V, so we use the formula P equals V squared over R to find P. P equals 25 over 50. That is half a watt. Next, suppose we have a circuit with resistors in parallel. One of them has a resistance of 50 ohms and a 10-volt source is driving the current. Can we find the power being absorbed by the 50 ohm resistor? And the answer is yes, easily. Because P equals V squared over R. That is 10 squared over 50, 2 watts. And finally, consider a circuit with a resistor of 30 ohms, a heater say, and a current of 10 amps. What is the power taken by the heater? Well, P equals I squared R. So P equals 100 times 30, which equals 3,000 watts, 3 kilowatts. And this is called the power rating of the heater. So we've seen how we can use the three formulae to find the power rating when two other values are known. But also, when the power rating P of an electrical item in a circuit is known, we only need to know one of the other three values, V, I, or R, in order to calculate each of the other values. Because since P equals VI, then P over V equals I, and P over I equals V. And because P equals I squared R, P over I squared equals R. And we have a formula for I, one for V and one for R, when we know P and one other value. Usually electrical equipment is rated for both voltage and power, as on this soldering iron. It's the same with this drill motor, and with this lamp, which shows 240 volts and 60 watts. 60 watts is the power rating, and it indicates the rate at which the lamp converts electrical energy to light. The other lamp, which is rated at 100 watts, when switched on is much brighter than the one rated at 60 watts. It is converting electrical energy to light at a higher rate. Power rating always indicates the rate at which electrical energy will be converted to some other form of energy. Light in the case of lamps, heat in the case of the soldering iron, and mechanical energy in the case of an electric motor. Resistors also absorb power, and so they too have a power rating in watts. These carbon resistors all have the same resistance, but the rate at which they use up electrical energy differs. So their power ratings also differ. The bigger the resistor, the higher the wattage they absorb. When resistors of higher wattage are needed, wire resistors are used. They usually range from 2 watts up to 100 watts, and special ones of even higher ratings are available for power ratings in excess of 100 watts. So, in electricity, the unit of power is the watt, and it is the rate of converting electrical energy to some other form of energy. In mechanical equipment, such as an automobile, say, we use horsepower to indicate the power rating. Since both the watt and the horsepower are rates of doing work, there's a connection between them. And in fact, 1 horsepower equals 746 watts. Finally, a word of warning. This is a sight you should hope never to see again. An electric conductor is smoldering. But it can happen, like this. Most conductors use the power they absorb to make heat, but they are usually electrically insulated. And this insulation also tends to keep in the heat generated, so that unless we are careful, the conductor may get overheated and damaged. For this reason, the currents allowed to pass through electrical equipment are limited, so that the heat generated is also kept within safe limits. Neglect this precaution, and the most disastrous and potentially deadly consequences may follow. And that's all we wish to say in connection with electric power. We saw that work is done whenever a force causes motion. And we saw that power is defined as the rate of doing work. In electrical circuits, power is equal to voltage times current. volts times amps, and is measured in watts. We saw that electrical equipment, including resistors, have a power rating which indicates the rate at which they will change electrical energy into some other form of energy. And we saw that there is a relation between watts and horsepower. In the next part, we will discuss the subject of alternating current.